But finding them, determining where they're going, using our planetary science aspects and researchers to learn more about them is all a part of our overall program, because planetary defense, frankly, is applied planetary science. And the two have to work together in this endeavor to protect Earth from a future impact. Thanks, Karen.
All right, Lindley, thank you so much. We will move on to Tom Statler, one of our DART program scientists.
Thanks, Karen. Good afternoon, everybody. As Karen said at the beginning, the Double Asteroid Redirection Test is a test. We're doing this test when we don't need to on an asteroid that isn't a danger, just in case we ever do need to and we discover an asteroid that is a danger. We're doing this test at a double asteroid, a binary asteroid, the larger asteroid Didymos being orbited by its smaller moon, Dimorphos. This is the perfect natural laboratory for this double test, because there are two tests in DART. The first test is the test of our ability to build an autonomously guided spacecraft that will actually achieve the kinetic impact on the asteroid. And the second test is the test of how the actual asteroid responds to the kinetic impact, because at the end of the day, the real question is, how effectively did we move the asteroid, and can this technique of kinetic impact be used in the future if we ever need it to? So this double asteroid is the perfect place for this test, because from our point of view on Earth, we see Dimorphos crossing in front and behind and in front and behind of Didymos every orbit. That's observable telescopically. Even though we can't see the two objects separately, we can see the total light from the pair dip just a little bit, twice every time around the orbit. And that's how we know from telescopic observations that the orbit is 11 hours and 55 minutes and has been absolutely solid for probably thousands of years, if not longer. But our DART spacecraft is going to impact Dimorphos at a speed of 14,000 miles per hour, changing its speed by perhaps 1% or so, and changing the period of that orbit. Just like if you dropped your wristwatch and damaged it, it's not going to keep necessarily the same time anymore. We're expecting that clock, that orbit, to run just a little bit faster. And you might not notice it right away, but in the weeks and days and weeks to follow, you would notice that your watch is running fast, and we will notice that the binary asteroid system is running fast. We'll be able to see this by using the same techniques, telescopes on Earth, observing this binary system for the weeks following the impact. And we'll have telescopes on every continent on the Earth observing the Didymos system. Not only that, we'll also have telescopes in space, the Hubble Space Telescope and the James Webb Space Telescope, and even our Lucy spacecraft will be observing the Didymos system close to the time of impact to see if we can see some brightening from the dust and debris ejected into space. And we also have, courtesy of the Italian Space Agency, the LICIACube CubeSat, which was deployed from the DART spacecraft on September 11th. LICIACube is flying on its own, controlled by the Italian Space Agency. LICIACube will follow DART about 3 minutes behind, also passed by Dimorphos at a safe distance of about 55 kilometers, and we're looking forward to successful images from the LICIACube spacecraft. But even with all of those observations, Dimorphos is a tiny asteroid. We've never seen it up close. We don't know what it looks like. We don't know what the shape is, and that's just one of the things that leads to the technical challenges of DART. Hitting an asteroid is a tough thing to do, and you'll hear about that in a minute. I'll turn it back over to Karen.
All right, thank you so much, Tom. Next up, we have Ed Reynolds, the DART project manager at APL.
All right, thank you. Good afternoon. We launched DART just almost 10 months ago, last November, and since then we've been working really hard for this moment. We've been really focused on the overall spacecraft, getting it ready for impact, making sure that the ground systems are ready for this to flow data during the impact day, and then also preparing the team to be ready for impact and then any contingencies that could occur during impact day. So we had a great launch. We've launched out of Vandenberg Air Force Base right around Thanksgiving, and we had a terrific trajectory that required very little correction maneuvering. And so in December, we went into 1 month of commissioning the spacecraft, and that went very smoothly. And what we can say at this point is that all subsystems on the spacecraft are green. They're healthy. They're performing very well. We have plenty of propellant and we have plenty of power. After we commissioned the spacecraft, we started focusing on the bits and pieces of SmartNav and just making sure that all those bits and pieces were in place so that on impact day they all work together. We have proven that they are all working and that they are ready for impact. And you're going to hear a little bit about that from Lena next. And so the spacecraft's doing great. The ground system, we've been streaming. We've been doing a bunch of tests where when using the spacecraft, we've been streaming Draco imagery at the one image per second that you're going to see on impact day. And so this goes into the rehearsals, just making sure that the ground system can handle that throughput and that we can do things like overlay informative information that help us and help other viewers look at the sequence as we're getting closer and closer and closer. And so it's going to be exciting. And then finally with the team, we've been doing a bunch of rehearsals, and some of the rehearsals are very nominal, like this is what we expect on impact day. But then we also get into the contingencies, and we've been doing rehearsals where we introduce unknown contingencies to the team. And we watch their behavior, and we make sure that they are truly trained up to handle the nominal situation and then any contingencies that occur. So at this point, I can say that the team is ready, the ground systems are ready, and the spacecraft is healthy and on track for an impact on Monday. So thank you.
All right, and for our final speaker today, we have Lena Adams, the DART Mission Systems Engineer at APL.
Yeah, so I'll talk a little bit about what you're going to see in the next few days from DART, and then also we'll harken back to what Tom was saying, which is it is really hard to hit a very little object in space, and we're going to do it. So over the next couple of days, we're actually still performing some trajectory correction maneuvers to make sure that we're on the right path to hit the asteroid. We're also going to be putting parameters on board to make sure that we're really ready for terminal. Ed said we rehearsed a lot, and yes, we have. But as we go through the cruise phase, we update parameters on the spacecraft to make sure that we can actually hit the asteroid. And so in the next couple of days, we'll update those parameters. We'll do checks like streaming images back to Earth. And, you know, Tom mentioned that we did a lot of Draco imaging. We have over 200,000 images already on the ground from Draco. So we know it works really well. We have been able to detect the Didymos system. So we can see Didymos, the larger asteroid. We have not seen Dimorphos, and we really won't, not until about an hour prior to impact. But we can see the Didymos system. We see it really well, very clearly. That's actually what we're using right now to guide ourselves to the system. So in the next few days, we'll take more images of the Didymos system. We'll do trajectory correction maneuvers, and then at 24 hours prior to impact, it's all hands on deck. We'll have people in the mock working overnight, trying to make sure that everything is set and ready to go. And at 4 hours prior to impact, the spacecraft becomes completely autonomous. What that means is that even though we do have a full mission operations center where there's about at least 44 people all watching data coming down and telemetry streaming from the spacecraft has to do everything. It starts with detecting Didymos, the larger asteroid. It starts tracking it. It's starting to guide itself towards Didymos. And then at about an hour prior to impact, and some models say, 70 minutes, some other models say maybe 50 minutes or maybe even 40 minutes prior to impact, for the first time, it'll see just one pixel in the field of view of our camera, Draco, and that's going to be Dimorphos. And so at that point, this is when we switch from guiding towards Didymos to guiding ourselves into Dimorphos. We're going to execute a bunch of maneuvers, all autonomously. The spacecraft points the solar arrays at the sun, streams data back to Earth, basically video, 1 image per second. So on Earth, we'll be actually able to watch, us stopping to go towards Didymos, and now we're tracking this new asteroid, and that's our target. So then a little bit after that, we're going to precision lock, and you'll hear us say that in the mock because all of this is going to be streamed on NASA TV. So you'll hear us say it, we're precision lock, which means we are now starting to ignore Didymos and we're going to Dimorphos. So, and then at 2.5 minutes before impact, SmartNav, which is the autonomous algorithms that have brought us to that point, is going to turn off, and we're just going to point the camera and take the most amazing pictures of this asteroid that we're going to see for the first time, and we don't know what the shape is, and then impact. It'll say loss of signal, and we'll celebrate. So I hope you're all out there. Back to you, Karen.
Thank you so much. We will start taking questions. I plan to start in the room, so if those of you who wish to ask a question can make your way to the microphone, please do. If we don't have anyone, so I don't see anybody standing up and jumping at that opportunity, we will probably go to the lines right away. But before we get there, I will say this, that Lena just mentioned that you can see it all on NASA TV. NASA.gov/live is the place to watch that broadcast starting at 6 o'clock on Monday, September 26th. And we will also, if you navigate your way to the NASA TV media channel, be showing just that Draco imagery starting at 5:30. So just a live feed of that as well. So with that, let us switch to the phone lines, please.
First question comes from Marcia Dunn from Associated Press. Your line is open.
Yes, hello. One quick question and one other one. Is there any possibility of manual intervention if the autonomous navigation isn't doing what it's supposed to do? Can ground controllers jump in and right it to the right asteroid, for instance? And I'm wondering also, perhaps for Mr. Johnson, what other tricks might be up scientists' mission planners' sleeve for deflecting or deflecting an asteroid? Besides impact, what are some other methods that are under review, if not by NASA, by others around the world? Thanks.
So we'll start with Lena Adams, and then we'll move on to Lindley Johnson.
All right, this is Lena Adams, and yes, of course, so the whole point of having people in the Mission Operations Center at that point is to be able to intervene if necessary. The one-way light time to be able to send a command to the spacecraft is only 38 seconds. So we have 21 contingencies that we plan for, that we're ready to execute in case something like that comes up. For example, the most simple one is that if we're seeing that Dimorphos is too dim in our field of view of our camera, and we wanted to increase the exposure time. Other ones do involve basically saying this asteroid is not the right one, and please switch over and start guiding yourself to the right asteroid, because we do have that video feed back to the ground. So yeah, we plan for all these things and we're ready to intervene, and we have been rehearsing this for quite some time. Lindley?
Yeah, Lindley Johnson, the Planetary Defense Officer. Yes, DART is demonstrating what we call the kinetic impact technique for changing the speed of an asteroid in space and therefore changing its orbit. But other concepts have been studied. We have a list of 3 or 4 that in the future we'd like to test. This demonstration will start to add tools to our toolbox of methods that could be used in the future. And we need several of them because the circumstances that we might face could be quite different. And we need an assortment of tools depending on the scenario. How far into the future have we predicted this impact? What is the size of the asteroid that we need to deal with? What is the orbit that it's in? Because some orbits are a lot tougher to get to than others from the Earth. So we need to build up a toolbox of different techniques. Some of the other things that have been studied are what we call a gravity tractor, which is just taking a spacecraft and station keeping with the asteroid and using nature's tug rope gravity The mutual attraction between the spacecraft and the asteroid will slowly tug that asteroid out of its impacting trajectory into a more benign one. Of course, a technique like that takes longer to implement, so we would have to have more warning time to be able to implement it. Other techniques, ion beam deflection, just shooting an ion engine at it for a long period of time, and slowly all those particles impacting the surface also change its velocity and therefore its orbit. Basically any technique that you can imagine that changes the speed, the orbital speed of the asteroid in orbit is a viable technique. And so we work with our colleagues, both in the other agencies within the U.S. government and internationally, to talk about these concepts and techniques and how we can collaborate to test them out. The forum has been set up, international forum set up, called the Space Mission Planning and Advisory Group, which is a forum for national space agencies. Some 18 of them right now are involved in same page in looking at technologies and techniques that could be used to deflect an asteroid.
All right, thank you so much. We will take the next question, please.
Next question from Gina Sansuri from ABC News. Your line is open.
Yes, thank you. Talk to me a little bit about what it takes to get video back from this impact. How complicated is that?
Is that for you, Lena?
Yeah, that sounds great. Yeah, I'd love to answer that question, and thank you for asking such a good technical question. So what it takes is a new type of antenna that we actually have on board of the spacecraft. It takes a new type of avionics that we're running through all our data. But what happens actually on the spacecraft is actually really fun. So we take an image of the asteroid, and then we process it through our computer, which crops it, then sends it over to the smart navigation system. Smart navigation system does a whole bunch of things with it to try to figure out where it's located in space. But at the same time, the image also gets cropped and then sent to Earth through our radio and then through our hard gain antenna and down to the Deep Space Network. A set of dishes that are actually going to be looking at us. Most of them are located in Australia, just because we're kind of on the southern trajectory. But we have a few dishes in Australia that both from the Deep Space Network and from the European, the ESA-TRAC, the European Space Agency dishes that are going to be looking at us and making sure that they can get this data down. So all of the processing happens in basically 2.5 seconds. So each one of the images has about 2.5 seconds latency that it gets received on the ground, plus, it takes 38 seconds to travel and 5 to 8 seconds to process. So what you're seeing on the ground is something that is probably about 45 seconds late. But that is still amazing because an image is coming in every second. So yeah, it basically looks like video stream coming in. It took us a lot of testing and practice.
Thank you so much. We will take the next question, please.
Next question is from Nell Greenfield-Boyce from National Public Radio. Your line is open.
Hey, thanks for doing this. So a question for Elena. If you guys miss, can you come back around again and take another go at it? And a question for Lindley Johnson. A lot of what the public knows about this stuff comes from Hollywood. I'm just wondering if you personally have watched shows like Armageddon and Deep Impact and sort of how the public should think about this test versus what they see, in their sort of more cinematic depictions of asteroid mitigation. Thank you.
All right, so I'm sorry, I got sidetracked on the Armageddon part.
It always sidetracks you, but well, let me handle the question. The question was what happens, if we miss what we call a missed approach. Now, through all the testing that we've done, and certainly what I've seen, the action by the APOL team on DART, I'm highly confident that we are going to hit on Monday, and it will be a complete success. But if there is a miss, then the first thing we've got to do is really figure out what happened. Why did we miss? So that'll be the first thing, is to safe the spacecraft, get all the information down from the spacecraft so we understand what occurred, and safe the spacecraft so that it's ready for future use. So that's what will happen in a miss, but I have every confidence that that's not going to happen. As for the Hollywood movies, this situation, asteroid impact, comet impact, has been a popular genre for science fiction books and movies for a long time. It captures the public imagination. But that's all Hollywood and movies. They have to make it exciting, and we find the asteroid only 18 days before it's going to impact, and everybody runs around with their hair on fire. That's not the way to do planetary defense. As I said, the most important thing we have to do first is find the population of the hazardous asteroids out there, and that is a big part of what our endeavor of the Planetary Defense Coordination Office and our partners across the agencies and the international community is. These surveys and right now ground-based telescopes that are searching every possible night, and we're finding about 3,000 near-Earth asteroids of all sizes every year, and we are about to cross the threshold of having found 30,000 of these asteroids. And it's entirely, we have the technology now to do this and find these objects years, decades, even a century before they pose an impact threat to the Earth. And that provides us plenty of time then to decide what is the best technique to prevent the impact, to put the asteroid in a more benign orbit so that we don't ever have to worry about that one anymore. So first we've got to find this entire population. We are currently working with ground-based assets, but the real way to do this is to have a space-based telescope, and we're working on that. It's called the NEO Surveyor mission. It is, in fact, having its preliminary design review this week, so this is a big week for planetary defense in our work here at NASA. And that telescope will operate in the infrared part of the spectrum, where the asteroids actually stand out more from the background of stars. And we can also determine the sizes directly from those measurements, and we don't have to take weeks and months of other data on these objects to understand what we're dealing with. So unfortunately, it's not the exciting Earth is going to end in 2 weeks scenario. It's a very focused and gradual way of working through this whole issue, understanding what's out there, then determining what you can do about it with tests like DART, and then working with our partners, other space agencies around the world to determine what's the best technique and what space agency is going to do what in this campaign that would actually be undertaken to deflect an asteroid in space should it become a real problem.
And I think Lena wanted to add something.
Yeah, so Lindley, thank you for taking the first part. So one thing I wanted to add is that I mentioned earlier the contingencies that we have on board. And that's actually we have 21 contingencies. Number 21 is missed impact. And what will happen in case there wasn't a missed impact, you will see the team will just sit back down, because you can imagine we'll all be anticipating, and in the last couple of minutes we're all going to be standing up waiting to see us hit an asteroid. But we're going to sit down back into our seats, and we're going to start preserving all the data on board about why we missed. And we have time with our deep space network right afterwards to be able to actually get all that data down. And then we'll start conserving propellant, and we'll start looking for the objects to come back to. So that's the plan.
All right, we will go on to the next question.
Next question from Bill Harwood from CBS News. Your line is open.
Hey, thank you very much. Can you hear me okay?
We can hear you. Yes, Bill.
Okay, thanks. I'm sorry. I recall a paper in Science, I think, earlier this summer about OSIRIS-REx and the sample collection process at Bennu, and the nature of the surface of that asteroid was such that there is somewhere, if they hadn't fired their thruster, they might well have just sunk right into the asteroid. It was so, the rocks are so loosely bound. It's probably apples and oranges, but just out of curiosity, if a high-speed object like DART hit an asteroid like Bennu, A, what would happen? And B, do you know that's not the case with Dimorphos? I don't know enough about that asteroid to know if that's a dumb question or not. Thanks.
Great. Tom Statler's going to take that one for us.
Yeah, this is Tom Statler. A lot of great questions in there, and a lot of great questions that the DART investigation team has been working on for years to study different materials and to bring to bear the cutting-edge computational simulation techniques that we have to be able to simulate what actually happens when a spacecraft hits an asteroid at 14,000 miles an hour. And our view of the range of possible outcomes has really been opened up by our experience with the OSIRIS-REx mission at Bennu and also by the Japanese Hayabusa 2 mission at Ryugu, both of which found that the surface materials were almost fluid-like. There was so little friction and so little cohesion, they behaved, even though they were solid chunks, behaved almost like a fluid. And so that does open up the range of possible outcomes. If the surface of the asteroid is very comparatively solid, we'll get a smaller crater. If it's as friction-free as Bennu seemed to be, we might get a very, very large crater or large pieces, a large section of the asteroid being reshaped. And that's a big part of why we need to do the test, because every time we go to an asteroid, it's a surprise. It's a learning experience to us. We do not know exactly how these asteroids will behave because we don't have samples of real asteroids on the Earth. We have meteorites on Earth, but meteorites are just the strongest parts of asteroids that make it through the atmosphere and make it to the ground. And so really getting ground truth on how an asteroid behaves requires that we go to space to do the experiment. Now, for anything really, really surprising to happen, I mean, as you said, the tag stand, the sampler mechanism on OSIRIS-REx seemed to just keep going into the surface of Bennu, but we know that DART is going to be stopped by Dimorphos. For one reason, the density of the DART spacecraft is actually not very different from the density of an asteroid. And so there's no question that DART is going to run into a whole lot of material that can't get out of the way. And so that is going to make it stop. So the scenario where it goes straight through, that's just not going to happen. Also, there are ways, there are aspects in which we know Dimorphos, or at least we know Didymos, is not like Bennu. We're extrapolating and assuming for the moment that Dimorphos is similar to Didymos. But Didymos, for example, is a different composition. It's a different spectral type than Bennu. Bennu is a very dark carbon-rich object. Dimorphos has a reflectivity 3 times brighter than Bennu, so we know it's a different kind of object. It's also spinning very rapidly, and the dynamical studies show that Didymos has to be either higher density or more cohesive, or both, than Bennu. So a lot of things could happen, but we really do not expect Didymos or Dimorphos to be a carbon copy, literally, of Bennu.
And one thing I want to add, too, is that we're actually going to know the ground truth with the Hera mission arriving there in 2026, the European Space Agency mission that's going to be a follow-on to DART that is going to look at this crater and look at Dimorphos and really study the surface. And I think that'll be great for everyone.
Great. We have more questions on the phone line, so I'm going to keep going back there. But I do want people in the room to know that if you want to stand up, I will call on you at the microphone if you decide you have a question to ask. For now, please, let's take the next question on the line.
Thank you. Next is from Aylin Woodward from Wall Street Journal. Your line is open.
Hi, thanks so much. Just a couple of clarifications. So once you've locked on to Dimorphos, if you need to make a course correction, are you utilizing the hydrogen propellant, and are you utilizing those onboard thrusters? And then I just wanted to also clarify that basically a round-trip communique from the spacecraft to Earth and back would take a little over a minute, given that it's 38 seconds one way, correct?
Right to both. We're using hydrazine thrusters to perform all maneuvers in terminal. We demonstrated our next-C thruster for a couple of hours early on in the mission. That has been completed. Now we're using hydrazine only. So we have 12 hydrazine thrusters. That's what's actually going to be propelling us towards the asteroid. And then for your other question, that's right, 38 seconds. So multiply that by 2, it's over 70 seconds. So over a minute round trip light time. But what you're really looking for is the time that the images are going to come back to Earth. And so there's close to 10 seconds of processing, 5 to 10 seconds of processing on top of the 38 seconds of it, just round trip light time. Sorry, one way light time. Round trip, one way.
So,
Go ahead.
Just to add, on impact day, at the moment of impact, just so you're not confused, you're going to hear messaging that we've lost radio contact, and there's still going to be images coming through and being displayed once per second for about 8 seconds, and those are images that are traveling through space, and they've hit the ground. We've detected that we've lost radio contact, but those images are still working themselves through the pipeline and being displayed. So when we kind of have some guidance to the team that just so that no one's celebrating too early, that we'll get that message of loss of contact, and we'll still be seeing it. And we're basically, you'll hear Lena will say impact, and she may put other words around it, but
hopefully yes.
But that's where we have very high confidence that we did hit the asteroid, and that we can let the guard down on the Mission Operations Center, and people can relax.
Yeah, and of course you will also see the images of Dimorphos extremely close up. Our last image is probably going to be from about 2.5 seconds prior to impact. So the Draco field of view is actually going to be completely filled with this beautiful image of Dimorphos.
I do need to add one thing to that, since we're talking about that wonderful moment when impact will occur. The engineering team will be celebrating. Yeah. And the astronomers at that moment will be saying, okay, time to get to work.
That's true. That is very true. This mission has 2 parts. The first part is hitting the asteroid. The next part is actually measuring what happens afterwards, as Tom said earlier.
So for those of you on the phone, the first person who wasn't Lena who spoke was Ed Reynolds, and the second person was Tom Statler, so you know who to attribute information to. With that, we will go to our next question, please.
Next is from Dan Vergano from Grid News. Your line is open.
Hi, thanks for the name identifications. Dan Vergano, Grid News. I'm wondering if the impact happens and Dimorphos is diverted that 1% factor you talked about, what does it tell you about how much lead time or how much distance from Earth you need to deflect an asteroid about its size, moving about as fast as it is from hitting the Earth? And sort of a code of that question is, in terms of spotting those asteroids, what is the delay of NEO Surveyor, not at least 2 years, or mean in terms of being able to spot these kind of things coming in? Thanks very much.
Okay, this is Lindley Johnson and Arctic, those two. As I said, it's very scenario dependent on what the lead time is and would be needed, and depending on the technique. As I said, that any technique that changes the speed of the asteroid in its orbit about the sun is a viable technique. It's just a question about how much you make that change. So a kinetic impactor of DART size, well, DART is specifically sized to have the desired effect on Dimorphos, which is a small moon. If we were faced with an asteroid in orbit about the sun heading towards Earth, it would depend on the size of the asteroid, how much we would need to hit it with. In the case of a kinetic impactor, it would probably need to be larger than DART. And we also might hit it with several kinetic impactors, each having its own, stepping down the speed of the asteroid to affect the change. Other techniques might take longer or shorter, depending on the size. So that is all the kinds of things that need to be assessed once we are dealing with an actual threat. The second question you had was with the budget reduction in the NEO-Surveyor project. Currently, we have a budget that is over on the Hill for the appropriations. It will depend on what Congress does with that budget, of course. But that budget will allow us to launch not later than 2028 with NEO-Surveyor. That's about a 2-year delay than what we were looking at earlier, but luckily time is somewhat on our side in this business. A asteroid impact is an extremely rare event. Maybe once a century. Is there any asteroid that we would really worry about and want to deflect? And only maybe once in 1,000 years an asteroid the size of Dimorphos on average. But the important thing is to get the capability up and find them. NEO-Surveyor will be able to find the population of asteroids 140 meters and larger within about a 10-year period. And that's, a very short period in geologic time. And unless we happen to be particularly unlucky, I'm not worried about an impact in that kind of a time frame. But it's something that we need to get done, and so that we know what's out there and know what's coming and have adequate time to prepare for it.
All right, moving on to the next question.
Next question from Brett Tingley from space.com. Your line is open.
Hi, thanks for taking my question. I'm wondering, in the course of the development of the SmartNav system and the trajectory correction systems, did you conduct any hardware testing, like flight tests, so to speak, or was it all completely computational? Thanks.
I think I'll take that one. Yes, we have done a lot of different flight tests. Okay, first, of course, we've done a lot of testing on the ground because you shouldn't fly anything that you haven't tested on the ground. And we did a lot of testing on the ground with computer simulations. But once we launched, we actually have done quite a few tests where we were looking at stars and trying to fool the SmartNav system that 2 stars right next to each other are Didymos and Dimorphos and tracking them. We conducted those tests. And then recently, and that's something that we published in the news recently, is that we've been watching the Jovian system, so Jupiter and its moons. And we actually watched Europa exit from behind Jupiter. And we fooled our SmartNav that Jupiter was Didymos and Europa was Dimorphos, and we actually watched the separation happen. And why that is important is because in the last 4 hours during our terminal phase, when the spacecraft is completely autonomous, we're going to watch Dimorphos emerge from behind Didymos. So we already trained the system to do this in flight. So we're looking forward to it. I think we can do it.
Thanks so much. Continuing with the phone lines. Next question, please.
Next question from Jeff Faust from Space News. Your line is open.
Good afternoon. A couple quick questions, probably for Tom Statler. You talked about getting the measurement of the change in Dimorphos' orbit within days or weeks. Do you have a sort of a more specific estimate about how soon you might be able to know what the new orbit is? And then how quickly after the flyby do you expect to get images back from the LiCiCube spacecraft? Thanks.
Yeah, this is Tom. I'll take that. So I'll do this in reverse order. So LichCube is being controlled by OSSI right now. They are testing out their systems, and they will be taking images as fast as they can, storing them on board. The rate at which they're able to download their images depends on their exact state after the flyby. It depends on the availability of the Deep Space Network, and the Deep Space Network helps to communicate with and navigate with everything in deep space, and we have a lot of things in deep space, and we may have more things in deep space soon. But OSSI will be prioritizing early download of the images that have the best chance of showing us that we have a confirmed impact and the ejecta plume from that impact. But the data rate will be fairly slow, and so I don't think we should be expecting more than a couple of images per day on average coming back from LichCube. Now, on the other question, you were asking me to predict when we're going to get the first indication of the orbit change. I think it's fair to say that different parts of the investigation team have their own ideas about that, and they're competing with each other. I think the optical observers and the radar observers have a friendly rivalry to see who's going to get it first. I don't want to get into the middle of that debate, but I think I would be surprised if we had a firm measurement of the period change in less than a few days, and I would be really surprised if it took more than 3 weeks. But what that says is, again, we're doing the test because we want to understand how this asteroid is going to react, and we really don't know until we do the experiment.
Great. We will move on to the next question, please.
Next question from Alexandra Whitsey from Nature Magazine. Your line is open.
Hi, this is for Lindley. I want to follow up on the NEO surveyor question if I could. How much would NEO surveyor need to be allocated by Congress in this funding round to make it back onto a 2026 launch?
So we do have basic information about that, Alex. So why don't I follow up with you offline, and I will get you what information we can, okay?
Okay.
Thanks. So, though I'll give you an opportunity to ask a different question right now if you want, since I know you've been in the queue.
No, my others have been taken. Thank you.
Great, Alex. I'll follow up with you. Fantastic. Let us go on to the next question then.
Next question from Marcia Smith from spacepolicyonline.com. Your line is open.
Thanks so much. I was wondering if someone could provide a little more detail on what you expect to see from Hubble, JWST, and Lucy. I think someone mentioned that you'd be looking for images or some other spectra of the dust that might come up from the impact, but what exactly are you looking for, and what different wavelengths will each of these be looking at? I guess Hubble looks invisible and JWST in infrared, and what about Lucy? And how far from JWST will DART be?
Tom Staller.
I can take some of that, but that's that's quite an oral exam you gave me. I'm not going to remember all of those numbers, so I'll have to get that to you after the fact offline. So Hubble will be observing. So Hubble and JWST and Lucy will be observing starting before the impact to some number of hours, a varying number of hours after the impact. And I should back up 1.5 steps because, of course, as I said, the most important observations are those that tell us the period change of Dimorphos. But observing what's going on just in the first few hours after the impact, what we're looking for there is an overall brightening of the whole system, indicating how much dust and other debris got kicked up, because that ejecta goes into space and it is also lit up by the sun, just increases the total amount of surface area of stuff that's shining in the sunlight. And just being able to measure how much that brightening happens and when does it happen is a measure of something about the consistency of the material that was lofted up and how much there was. So all of these telescopes are going to be observing over that time. Hubble, I'm pretty sure, is observing in the optical region of the spectrum. Hubble is going around the Earth, and so half of the time it's behind the Earth. So Hubble won't actually catch the exact moment of impact. That's okay because we don't really expect anything to be really observable from the exact moment of impact. But Hubble observations will start about 15 minutes after the impact. JWST, because it has to readjust periodically to pick up new guide stars, may not be observing again at the exact moment of impact, but will pick up just a few minutes afterward. And Lucy will be observing from roughly twice as far away as the Earth is from DART and Didymos, from a different direction. Lucy will be observing with its LOLORI imager, which is very similar to Draco, actually, and it's only a 4-inch telescope, and so it will see very faint object brightening. LOLORI is also an optical imager. JWST, I would have to go and check with my colleagues to find out exactly which instrument and which camera, which wavelengths it's observing at.
And I can follow up with you offline again and see what information we can get you. But for everybody, if you check out nasa.gov/DART, we are going to be updating as soon as we get imagery and we find out more about it. We'll be putting things up there. And it looks like Lena has a follow-up.
I was going to give a number, which was we're going to be impacting Dimorphos at 7 million miles from Earth. So you can imagine that JWST and Hubble are going to be in that vicinity in terms of the distances.
Yeah, well, JWST is at the L2 point, which is a million miles out. So subtract 1 million miles and 5.8.
Yeah, so here miles. You go. You're welcome.
All right, we will take the next question, please.
Next question is from Alicia Sowers from Mashable. Your line is open.
Hi, thank you. I think this is for Ed. I'm wondering in terms of Monday, what's your probability calculation for hitting or not hitting the target? I'm just trying to better understand how likely it is that it will hit Dimorphos. And then if you could indulge us, what part of the event leading up to the impact really concerns you the most? And it's sort of like keeping you up at night as we get closer to it.
Let me start the last question first. So what concerns me the most is the weekend. So there are 44 people in the mock, and they're all, each one has a level of criticality, so as we go into the weekend, especially like Friday and Saturday, it's like you just want the team to stay safe, and so we built DART in the middle of a pandemic. We're still in the middle of a pandemic, and so you just want to make sure people are not getting sick or having family in distress with other issues. So the thing that I would like to see Monday morning is we have a fully populated mock and everyone is healthy and well rested and in the right frame of mind. So with regard to probability of hitting, we've been doing, since we've launched, almost continuously we do mission simulations, and we don't do them in a vacuum. We actually do a lot of measurements in space with the spacecraft. Like we point it to the exact attitude that we're going to be in terminal, and we do things like, let's do a lot of thrusting just because we have big long solar arrays, and let's see how they behave, and we collect that data, and then we take that data and we fold it back into our models, and we continue to do mission simulations with the new data and refining it. And Lena had talked about parameters, and so a lot of these, we don't do simulations just to do simulations. We do it to learn and to figure out what are the best parameters to have on the spacecraft as we begin. And as we kind of, the Dimorphos and Didymos, Dimorphos begins to reveal itself and how the algorithm behaves to what's revealed, we're going to get maybe some insight as to, hey, that looks like the mission sims that we did like 3 months ago. And so it's kind of a good place to really go and look at how everything's behaving, and should we adjust a parameter. And so we're with all of this rehearsal and with all these measurements, we're in a very, very good place to do this Monday's event. That said, Dimorphos is just barely over 100 meters in diameter. It's not very big. We're at 14,000 miles per hour. We're approaching something that we've never seen before. So, to quote the past, we do things because they're hard. We're at the point where technology is emerging so that we can use these emerging technologies to protect ourselves against these threats. And so that's why the T in DART is test. And so it's test and learn, and I think we've prepared ourselves for this moment. But I don't worry about the spacecraft. I don't worry about the algorithm. They're not what keep me up at night. I worry about my team. I worry about my daughters. And so I think we're ready.
Great, thank you so much. We are going to try and get to as many questions as we can, and we'll go to the next one, please.
Next question is from Tim Fernholz from Quartz. Your line is open.
Oh, thank you. Sorry, that question has been asked. Thanks.
So I think we can move on then, but thank you.
We'll move to the next question. Jake Robbins from the We Martians podcast. Your line is open.
Hey there. Thanks for taking the question. I'm just wondering about the AutoNav software. How much of that software was created brand new for DART, and how much of it is legacy software that maybe comes from other missions? I don't know if it's New Horizons or something similar.
I can answer that. So we actually created the software specifically for DART. It does not come from other missions. Smart navigation is based on some of the algorithms that are used in the missile world, just because, they're also interested in hitting small things in space. But this is the first use in space, and we had to change a lot of things to actually make it flyable.
Thanks so much. And on to the next question, please.
The next question is from Kenneth Chang from New York Times. Your line is open.
Hi, thank you. So now it's hit other in space successfully with Deep Impact and LROS. So I was wondering, how much harder is this one? Is it a lot harder because you haven't seen Dimorphos yet?
Oh, I'll take this one. Yeah, you're spot on. It is extremely hard for multiple reasons. Deep Impact and other missions, they really are looking at the asteroid. The sizes of those asteroids are much, much larger than what we're going to be hitting with DART. We don't really know what the shape of the asteroid is. We don't see it until the last hour, and that point is just a pixel in the field of view. I mean, at 3 minutes prior to impact, 2 minutes prior to impact, it is 42 pixels in size. That is, and you're moving extremely fast, and at that point, you cannot really send any commands in. So your system has to be very, very precise in how it's controlling the spacecraft, what information we're taking in from all the different sensors on the spacecraft, in addition to the telescope itself. So yeah, it's a little different.
All right, we have 4 more questions we'll be taking. We may go a little past the hour, though we might try to be quick on our answers if we can. Going on to the next question.
The next question is from Asia Farrington from KEB 9 News. Your line is open.
Hi, thank you. So you mentioned that it could take anywhere from days to weeks to figure out if this mission is successful. If it is successful, are there any plans to build more DART spacecraft for future use or for even future tests for larger asteroids?
This is Lindley. I'll take that. For the spacecraft part of the mission, we'll know immediately if it's successful, because it will have hit the asteroid. What Tom was referring to earlier was the observations that have to be taken to determine just how much effect it had on the orbit of the asteroid, which could take days or weeks. As far as if this is a successful or is we're going to build a fleet of DART spacecraft or something like that, well, this is just the first test of a technique to divert an asteroid. We want to test other techniques. I mentioned the gravity tractor and some other things earlier. But also, as I mentioned, an asteroid impact, a threatening asteroid, is a quite rare event. We don't know when the next one is going to be, which is why we have to be looking for them to determine that. But our strategy is to find that population out there with a mission like NEO Surveyor and know where all the potential hazards are, and then have sufficient time to then build the right actually campaign of missions to go out there. One of the first missions we would probably do is what we call a characterization mission, send the spacecraft out for at least a rapid flyby of the asteroid so we get a really good idea of what it is we're dealing with, so we're not having to do like DART is and not even see its target until almost before it hits it. And then be able to decide what is going to be the best technique to use against this asteroid. No, we won't have a standing fleet of DART spacecraft. Besides, when the next threat comes, technology will probably have moved on, and 30, 40 years from now, who can imagine what technology we might have available to deflect an asteroid.
Great, thank you. We will move on to the next question.
The next question is from Sabrina Ortiz from ZDNet. Your line is open.
Thank you so much. Just to clarify, will there be 2 live stream events that the public can watch, and are they happening at the same time? So the Draco images on NASA TV, and will the live video be on nasa.gov.live? And if both of them are happening at the same time, which would you recommend they tune into?
All right, let me clarify. Both are actually on NASA TV. However, one is on the media channel. So the quiet live feed of the Draco camera is starting at 5:30 p.m., I'm sorry, and it will be on our NASA media channel. The broadcast starts at 6 p.m., goes till 8 p.m. Did I get that right? No, 7:30, I'm sorry. Goes to 7:30, and it is also on NASA TV. I just gave the URL, which is nice and simple to find, which is nasa.gov/live. And I can't tell you which one to watch, except we're putting a lot of work into that broadcast, and I know it's going to be great. So that's my suggestion. Then we will have that imagery from the Draco camera as part of that broadcast as well, so you get a twofer by watching the broadcast. All right, we'll go to the next question.
The next question is from John Kelvey from The Independent. Your line is open.
Hey, great. Thank you very much. You did hit on some of these elements, but I was hoping we could kind of bring the threads together. I presume that if there were a threatening asteroid right now, you wouldn't feel confident building just a scaled-up DART to do a deflection mission. So what are some of the specific things you'd like to learn from DART that would, leave you with the confidence to make a kinetic impactor mission that could actually deflect an asteroid really threatening Earth? And are there any already known limitations on that? For instance, is that not the route you would use to deflect, say, a comet, but you would a smaller asteroid? Thank you.
Let me try to answer real quickly part of that question, and that is about the spacecraft operations and such. DART, will demonstrate the technology that could be used, the autonomous navigation capability, SmartNav, and having a camera like Draco on board. So the sort of the end-to-end system of the spacecraft will give us confidence that such a spacecraft could be built if there were a threatening asteroid discovered. The rest of your question is sort of dependent upon the characterizations of an asteroid. I don't know, Tom, if you want to add anything about that. We do need to learn more about the population of asteroids out there.
Yeah, I can take a little bit of that. I mean, yes, we need to know more about the populations, and so this is where where NEO Surveyor will be tremendously important, not just to find that population, to understand what is the range of different properties. As far as the DART outcome goes, I know that one of the things that I would like to know is the outcome from the DART experiment in line with what we expected on physical grounds, on simulation grounds, beforehand, because if it turns out that our expectations for how a solid object would behave, for example, ends up being very much in line with the way a real asteroid behaves, that means our physics is pretty good and we can use that to predict what we would do in a new situation. On the other hand, if the asteroid responds to the DART impact in a way that's totally unexpected, that might actually send us back to reconsider whether, to what extent kinetic impact is really generally usable. So we certainly hope to learn as much as we can. And being surprised is a good thing, because that's when you learn stuff, when your expectations are not met. So the DART experiment is going to be very exciting. As a scientist, I fully hope to be surprised by the results of the experiment, although as a planetary defender, I don't want to be too surprised.
Yeah, so I'll add just one more thing. There have been a lot of lessons learned for DART and for the operations team of how we would actually operate a mission like this, because the way it was designed was that it had a lot of other technologies demonstrating as well, and we would really design it for the kinetic impact in a way where we have many more guidance and control sensors that would be able to tell us more about the system. We would not have large floppy arrays because we want to keep the spacecraft as lean and as trim as possible. Also, we might want to go faster instead of bringing more mass. So these are all different things that you would have to study depending on what you want to do for real.
All right, thank you. We have 2 more questions. I'm going to take one more on the phone line, and then we'll take one in the room. So phone line, next question.
Thank you. And the last question is from Sarah Lang from Christian Science Monitor. Your line is open.
Hi, I'd like to ask, and this can be for anyone, you to articulate what feels the most innovative about this approach to NASA scientists. I mean, being the first planetary defense mission that's been conducted. And does it open the door for future opportunities within this field?
Anyone?
You know, I'm kind of the layperson of the group here, so the thing I found the most interesting is just the test itself. So if you just went and hit an asteroid out in space, you'd hit it, you'd change its velocity by 1%, but the problem is with the trajectory and what we know about that asteroid, the uncertainty is so great that you would not be able to measure that 1%. The unique thing about this approach is the moon. You've got a moon asteroid around a bigger asteroid. You can measure the period of the asteroid very precisely, and we're like 11 hours and 55 minutes, and you can get that looking at light curves. And then you hit it, you change its velocity, you change its orbit period. We think we're going to change it about 10 minutes. Our requirement's about 73 seconds, but we actually think we're going to change it by about 10 minutes. Looking at the light curve, you can measure that very precisely. And so it's just the whole unique aspect of this whole test that is, to me, it's like just when I first heard about it, and I knew about the error bars on asteroids and their orbits, and then I heard the whole moon approach, I thought it was brilliant.
Great, thank you so much. Oh, you want to add more? Tom Statler?
This is Tom. Let me go after the broader picture of how it's innovative, because we haven't had an opportunity to say that yet. We are moving an asteroid. We are changing the motion of a natural celestial body in space. Humanity has never done that before. And this is stuff of science fiction books and really corny episodes of Star Trek from when I was a kid. And now it's real. And that's kind of astonishing that we are actually doing that, and what that bodes for the future of what we can do as well as our discussions of what as humanity we should do. It opens up an amazing frontier that is very exciting.
And also just how exciting it is for the public, right? To be able to, here's a mission that you can really get behind and really can understand very easily, and just how fun it is to move an asteroid in space.
All right, we're going to end with one last question in the room. If you'd identify yourself too, please.
Hi, I'm Zach Savitsky from Science Magazine. Tom, just following up on your answer from previous, do you have any, or can you elaborate on how NEO-Surveyor could tell us about the internal structure and composition of potentially hazardous asteroids? And are there any plans for doing that sort of assessment prior to future kinetic impacts?
So NEO-Surveyor would give us part of the story, because NEO-Surveyor, when it flies, will give us the ability to, first of all, find lots of objects, and secondly, measure their sizes directly, which we haven't had an opportunity to do. And you combine that with regular optical telescope data, then you very quickly get the distribution of reflectivities for all of these objects. So you get immediately a survey of sort of different mineralogical types in a very, very rough way. Then, if you're ever in a situation where you need to respond to a dangerous object, the most important thing you would need to know would be the mass. Now, if we have by that time also really good information from other missions on how mineralogical types correspond with density, then knowing the density and the volume, the size gives you mass, and maybe that helps you respond in a way that may not be quite so reliant on sending a reconnaissance flyby, for example. But every piece of information is a partial step to where you really want to be, but it's definitely a contributor, even though it wouldn't be the answer to all of our questions.
Thank you so much. I want to say thank you to everybody for joining us today. We are going to wrap up at this point. If there was a question you didn't get answered, please feel free to reach out to our press team here at NASA headquarters, and we will get you an answer. And in the meantime, get ready to watch our show at Monday evening at 6 o'clock on nasa.gov/live. Additionally, as I mentioned, we will continue to have updates about imagery at nasa.gov/DART after that. So both of those URLs are the places to keep informed. And thank you so much. Looking forward to Monday. Thanks.
We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations of